Sandman here. This is lecture 1 of my instructional series. Today I'm going to be discussing pen tumbler locks. The pen tumbler lock design was invented in ancient Egypt between 2,000 and 4,000 years ago. It was adopted by the Greeks and it was further refined by the Romans. However, there wasn't much development in the pen tumbler lock design from the Roman Empire up into modern Western Europe. It wasn't until the pen tumbler made its way to the New World in North America that we see the modern refinements that we are so accustomed to today. In Europe, they utilized the pen tumbler lock in what's called a Euro profile cylinder. It is a large double-sided cylinder allowing the resident to lock their door from the inside and the outside utilizing the same key, or alternatively a master key. But what stands out the most about this style of pen tumbler lock is that the Bible or the pen stack of the lock is actually at the bottom of the plug and the opening of the keyway is at the top. Whereas in North America, this is a typical key and knob cylinder and our Bible is installed at the top of our plug and the opening of our keyway is at the bottom. The North American pen tumbler lock has been refined to the point that we have figured out that when installing pen tumbler locks that are exposed to the elements, it leaves itself vulnerable to water, debris, and therefore corrosion and damage to the pen stack and the springs. That is why all North American locks are installed with a pen stack to the top. The anatomy of a pen tumbler lock are seen here in this physical diagram. We have a shell, also known as a lock core. We have a plug. We have key pins. We have driver pins. And we have springs. Most North American pen tumbler locks have anywhere between 4 and 6 key pins and 4 and 6 driver pins. For every key pin, we have a driver pin. Another design of the North American pen tumbler is going to be a rim cylinder. That is held into most mortise cases or door locks using set screws on these corrugated sides here. Alternatively, we have mortise locks that are threaded that go into mortise cases, such as this Adams Wright style commercial mortise case. This is what's most common in North American commercial doors. We see this key and knob cylinder primarily in quickset and Schlage style residential doorknobs. This particular doorknob has the cylinder on the inside of the knob, hence the term key in knob. Lastly, it is very common to see padlocks and door cylinders with a figure 8 design on the face of it. This would indicate that it is an SFIC or LFIC. SFIC meaning small format interchangeable core. LFIC meaning large format interchangeable core. The smaller format interchangeable core are simply pen tumbler design cylinders. However, they've been built so that the operator can easily remove the core to replace the lock itself without having to repin the lock. This cuts down on time and cost for the contractor. I have a control key and I have an operating key. The control key allows me to actually remove the entire core from the lock body so that I may replace it with a different lock that is keyed to different set of keys, while the operating key allows me to function the padlock as normal. Going back to the topic of our key pin and driver pin with inside of our pen tumbler design, we can see the pen tumbler design as this is the face of our lock. Imagine if we cut away the face of the Bible of our lock, exposing the spring, the driver pin, and the key pin. In order for our pin tumbler design to work and be functional, we have to not only apply upward force, lifting our key and driver pin against the tension that is pushing back from the spring, but we have to provide rotational force inside of the plug. By providing rotational force inside of the plug and lifting against a key pin, we'll eventually find what's called a shear line. The shear line is the moment of impact, or rather separation, where a plug separates the key pin from the driver pin. Most North American pin tumbler locks all have similar driver pins in size and shape. However, the key pins are all different sizes. That is what makes a combination of a particular given key. If I were to look at this key here, we have shallow cuts, we have another shallow cut, and we have a very deep cut. And then we have another cut that is not as deep, and then another shallow cut. That is what's called the bidding. This creates a combination that makes this lock difficult. If I had all shallow cuts going across that were all the same depth, I could just stick a very simple tool, such as a toothpick, while applying rotational force to the plug to pick open my lock. Alternatively, if I had nothing but deep cuts going across this particular key, and all the pins were therefore deep pins or longer pins, I could still stick a very similar tool like a toothpick, but much thinner, while applying rotational force to the plug of the lock and easily pick my lock. By applying a complicated key bidding from low to high to low to high to low, this is what makes access control more complete. It is much more difficult to pick a lock that has alternating bidding between low, high, or deep and shallow cuts. Another form of security and key control is what's called the keyway. The keyway is the shape of the key and how it enters into the plug of my lock. Some keyways are more restricted than others. The ones that are restricted so much that the milling of the key or the warding of the plug overlap each other are called paracentric keyways. Paracentric keyways make it extremely difficult to pick the lock. This, going back to our pin tumbler lock, we have the key pin, we have the driver pin, and it requires two tools to operate a lock using a single pin picking or raking method. The two tools required to pick this lock are going to be a lifter pick or a rake pick and a turning tool or tension wrench or tensor. I'm going to take my turning tool and I'm going to place it at the bottom of my plug. I'm going to take my lifter pick or my rake and I'm going to touch the bottom of the key pin, and I'm going to lift each pin individually or all at the same time and hope to get an illicit effect out of my core. I'm trying to rotate the plug at the same time I'm lifting the pins, hoping to find a shear line so that I could eventually rotate the plug. We're going to take another look at our pin tumbler lock, but from the inside. If I insert my key and I rotate 90 degrees and I remove my plug retaining tailpiece, I can insert a plug, and this will help maintain my driver pins and my springs from falling through the hole in my cylinder. I have now removed the plug, and we can now see the top pins as they are sitting in the plug. As I insert the key in and out of the plug, we can see some of the pins rise and fall. That is all due in part to the key bidding. On my key bidding, I have different size cuts, and inside the plug, I have different size pins. The pin tumbler lock design is in fact a combination lock. You have to have a key that has the right combination to align the pin tumblers, or the pins, so that they are even across the plug of the lock. If I were to insert the incorrect key with the incorrect bitting, what we would have is incorrect placement of the key pins. Here I have inserted the incorrect key, and now we have several key pins sticking up and several key pins depressed inside their hole still. These holes would be filled with the driver pin, and alternatively the driver pin would be placed too high up and we would not be able to rotate our plug. Inside of our lock cylinder, we have our driver pins and our springs. I will remove them now. Pin 1. As you can see, it is the driver pin that is first exposed to our plug, and then behind that is our spring. I can continue to remove these in order. And you will notice that typically in North American pin tumbler locks, a lot of our driver pins are all the same height. It is not necessary to have different size driver pins for a proper key bitting. However, there are different types of attacks on a lock that would take advantage of similar size driver pins that we must be aware of. We can talk about that in future videos. The reason we are able to pick a lock is not simply because we are replicating a key with any given pick and turning tool. In fact, the reason we are able to pick a pin tumbler lock is due to manufacturing tolerances. During the manufacturing process, the lock manufacturer has to be able to drill perfectly sized holes in line with themselves on a plane that rests along a cylinder. Drilling any type of hole with accuracy on a cylindrical object is one of the hardest things anyone can do in the steel manufacturing process. Due to these tolerances that we find in pin tumbler locks, we are able to manipulate that. If I have a cylinder, and here is the face of my plug, and I have holes drilled into the top of my plug, and I were to take a line and draw it perfectly down the middle, we would see on a very microscopic level, not seen to the naked eye, but measured, that these holes are not perfectly in line with one another. There are multiple reasons for that. Sometimes it's just because there is a wobble in the drill bit. It could be that the drill bit is not the correct size. It could be the drill bit is starting to dull. It could be that the jig that is designed to hold the plug is starting to loosen and is no longer holding the plug securely. But primarily, we are taking advantage of the fact that there is a 0.002 of an inch tolerance, plus or minus, in the steel manufacturing process. That means, regardless of the diameter of the hole or the spacing of the holes with each other, there is going to be 0.002 of an inch plus or minus in tolerance. This is what we would call slop. This allows us to take advantage and create what is called a binding order. Binding order is the order at which pins start to bind and set with inside a pin tumbler lock. If I were to just apply upward force against my key pin, while not applying rotational force on the plug, I would feel the sensation or feedback of the pin telling me that it is springy. This is due to the spring counteracting pressure against the driver pin, which is also applying force against the key pin. However, if I apply rotational force using a turning tool, my finger right now acting as that force, and I start to apply upward force or tension against my key pin, I am going to feel what's called binding pressure. This binding pressure is the plug forcing itself against the key pin. I'm able to feel this binding pressure due to the manufacturing tolerances in the manufacturing process. However, not all key pins are going to feel binding. We are looking for one pin to bind. If I am using a North American style pin tumbler lock, such as the Schlage SC1 keyway, it is typically going to be keyed with 5 key pins and alternatively 5 driver pins. If I apply rotational force against the plug while it is inside the lock, I will not be able to get all of these pins to bind necessarily at first. I will most likely get 1 or 2 or maybe 3 pins to bind. The ones that are binding, the ones that are providing the most resistance, are the ones that I want to pick first. The ones that are springy, that are not binding, those are the ones that I can avoid, as trying to lift those will accomplish nothing in my goal. Another thing is that as I go to seek a binding pin, I may decide to start with the first pin and then move to the second pin and then move to the third pin. I'm looking for springy or binding, and then move to the second pin. Is it springy or binding? And then move to the third pin. Is it springy or binding? Once I have found that binding pin, I will lift that pin until I feel or hear or see movement in the core. That will look something like this. So let's pretend this is pin 3. Let's pretend this is the third pin that I have investigated with my lifter pick, and it feels to be binding. While applying rotational force, I am lifting with my key pin, and it is binding. It is continuing to bind until I felt movement in the core. I do not want to overlift my pin. I do not want to overlift my pin because I will not be able to rotate my plug correctly. I only want to lift my pin just enough that I either see, hear, or feel movement in the core. That tells me that my key pin is set. I alternatively know that my key pin is set when there is no more springy tension against my key pin and there is no more binding tension against my key pin. This particular pin has been set, while none of the other pins in my plug have been set. It is then my goal to maintain my rotational force while investigating the rest of my key pins with my lifter pick or my rake, and I am searching for more binding pins. Once I have set all 5 binding pins in this particular 5-pin tumbler lock, the plug will fully rotate. If during this process, though I have set 1 or 2 pins, if I accidentally lessen my rotational force while in that process, I will also drop my pins. Alternatively, if I overlift just 1 single pin, I will not be able to rotate the plug of my lock. All the pins have to be set perfectly at the shear line, separating the key pin from the driver pin.